has been working, Sugu has been working in databases and this field, I think, for decades at this point. Um, I first found out, I first met Sugu while I was working at Slack when we were working on integrating Vitess, which is MySQL sharded technology that Sugu co-authored while at YouTube to solve a bunch of scaling problems. And now Sugu is working at Multigres, working on Multigres at Supabase. Supabase is like a Postgres development platform that I'm sure a lot of you are familiar with. And Multigres is their sharded Postgres solution that they are currently working on. So I guess I'll hand it over to you, Sugu, to talk about the rest.
All right, thank you, Arka. Let's see. Can you see my screen? My screen
Yes.
share.
Yes.
Awesome. Okay. Uh, I was preparing that while you were talking, making sure it worked. I have two screens, so I had to make sure the right one was getting presented. Cool. Yes, as Arka said, just to add a little bit, I actually was on a sabbatical, uh, and I had no plans of coming back. But over during that time, I kind of started getting interested back in technical work, and I found that Postgres is gaining momentum. And one of the companies that I was helping out actually had a huge outage, and that made me realize that this scaling problem is still not resolved for Postgres. Just so something like Vitess is actually totally needed, and so that is kind of a very short history of what happened, and that's why I am here. Um, cool. So I will try to breeze quickly through some of the content that I have, and I love Q&A, and even though that's not going to be recorded, but I think that will be the more important part of this presentation. So, what is Multigres? I'll give you a two-sentence overview of Multigres, and then I'll move on a little bit about, we'll geek out about a few things, and then I'll come back to Multigres. So, Multigres is essentially Vitess for Postgres. In case you have not heard of Vitess, Vitess is a sharding solution that solved scalability for MySQL. And what we are going to do now is essentially do the same thing for Postgres. But there's going to be some differences, and I will talk about what those differences are. But before going into it, I do want to talk about our philosophy, how we approach distributed databases, we have very strong opinions about how they should be. So I'll talk a little bit about why we think the way we think, why we do what we do, and how we do it. So before I go, a question. What do you think are the superpowers of a relational database? Uh, if you, I don't know if this is interactive, but if it is not, I will, uh, I will give my opinion of what I believe is the superpowers of a database. So the superpowers are, one is transactions. Why are transactions important is because if you don't have transactions, your application is going to be extremely complicated because updating two things at once, having an all or none semantic is extremely hard if you're working with storage. And the databases solve this problem beautifully, and that makes your application a lot simpler. And over time, transactions allow you to build really, really cool features in your application. If you don't have transactions over time, the number of features you can build in an application kind of gets limited. I don't know how many of you, this is something I've noticed. Now I've now come to the point where I go to a website and then just by looking at how that site behaves, I can tell that they are not using a very good database underneath or a very good data store underneath. There are some big e-commerce sites. You go there, you click on something, parts of the screen render, and then some parts are spinning, waiting, to go access whatever data is needed to present. So all that are signs of people not using, a good database underneath. Maybe they are using NoSQL. I don't know what's going on, but I can usually tell, because those things at the end of the day, that becomes the bottleneck. The next one is indexes. Uh, if you have indexing, then you can quickly get to your data, and databases do this extremely well. And the last one are joins. If you don't have joins, then you'll be making multiple round trips to your database to fetch the data that you want. So some people say SQL. There are lots of opinions that people say about what is great about databases. But if you go to the core of what are the most important operations that a database does for you, it's the combination of these three things that make a relational database extremely powerful. So if you have other opinions about this, we can talk about this during our discussion. So why do I talk about databases from this approach is because we have to keep this in mind when we are going to talk about sharding. When you say, okay, I'm going to shard my database, you have to make sure that these three things work well in your sharded system. And if you design your sharding system or the way you distribute the data without taking these three things into consideration, then your sharded system is not going to work well. And that's the reason why you cannot build these features elegantly in, for example, a key value store, because key value store tends to randomly distribute things that makes it very hard to optimize these things very well. All right. So the databases, I always say, it's a magical tool, but remember that there is no magic. Even if it is, so that means that if something looks expensive, it probably is. So you have to be very careful about what features of a database to use. So if a feature is cool, you have to think about how did they make it cool? Like did they find a really efficient way to do it, or are they just brute forcing it under the covers? Because if they are brute forcing it under the covers, it's probably not going to scale. So that's something to keep in mind while using databases, because databases offer some very, very cool features, but not all of them scale well. Okay. So here is a quiz. Everybody knows ACID, I assume, because you're all from the database world. Many of you must have heard of the CAP theorem. And just to give you a brief, in the past, ACID and CAP never came together because databases were generally monolithic. And the CAP theorem was introduced by Eric Brewer because key value stores were distributed and people wanted consistency, availability, and data to be distributed. And he said, no, that's impossible. So he introduced this theorem to basically tell people, don't expect everything from a distributed data store. Unfortunately, he paddled back on this when Google released Spanner, which I was very disappointed about because he said, oh, CAP theorem is not applicable to Spanner. Actually, it is because CAP theorem is based on the laws of physics. You cannot change the laws of physics. So there is actually a corollary to the CAP theorem called the PASELC, I think, which basically states that if your system is distributed, yes, even if there is no partition, there is a price to pay. And that price is latency. So in other words, if you're going to distribute data, you are going to incur high latency, and that can affect your database performance. And now we are going to talk about distributed databases. And now that we are distributing databases, we have to talk about the CAP theorem again, not from the point of view of things being partitioned, but more from the point of view of what are the latency costs that we incur by distributing our data. So on the left side, there's ACID. In this, I'll make a few clarifications because I have been in the database world for a long time. I confused I was confused about these properties because people in English tend to misuse them. For example, I say I want this, somebody would say, I want this to happen atomically, but they don't mean atomically, they mean actually isolated, right? So what is the difference between atomic and isolated? So there is a lot of confusion about that. So I'll give you a very quick overview of what these mean. Atomic means all or none. Either the entire transaction happens or it doesn't happen at all. The perspective here is if a transaction starts today and completes tomorrow, it is still atomic. But if it happens like this, what it is not is it is not isolated. So that is the difference between atomic and isolation. Isolation means all at once. The entire thing should appear as if it happened all at once. So in other words, if a transaction starts today and completes tomorrow, you don't see that transaction until it completes tomorrow. So that is the difference between atomic and isolated. And durable is obviously self-explanatory. You don't lose your data after it has been committed. So the reason why I bring these together is the quiz is which properties on the left associate with which properties on the right is the question. So atomic is a consistency property. That is very obvious. So what this means is in the terms of CAP theorem is if two rows are in different places, that means that you are going to pay the price of availability. So if you're going to do a single transaction that is in two different nodes, it's going to take longer than the transaction being in one node. So far so good. Consistent. So here is this is kind of funny. The acid consistency has nothing to do with cap consistency. They are completely different things. Acid consistency is things being consistent with each other, like foreign key relationships, relational rules being maintained, like all that stuff. The cap consistency deals with read after write consistency, which means that I've written something, then I try to read it back. Will I get the same row? So that is cap consistency, which is different from the acid consistency. So acid consistency has nothing to do with the cap theorem. Isolation is also a consistent property, which means that if things are distributed, it is very hard to project it as if all of it happened at once. Durability previously was not a consistency property, but now it has become one. And the reason is because in the past, durability, if your data went to your hard disk, it was considered durable. But in today's world, things are considered durable only if the data is in multiple places. So the distributed durability consensus protocols are used to ensure that your data is not lost. So that again now becomes a distributed storage problem. And again, that is another consistency property. So what does this all mean? All this means that a database, the ACID properties of a database, essentially what they want you to do is what it's saying that you have to keep them together. If you distribute them, it is bad news. It's not a good idea to distribute it because if you distribute your data, you're going to lose consistency, or if you want to keep your consistency, you're going to lose availability, which means that your database is going to get slower and slower. And if you are in a high performance OLTP situation, the way this manifests is in terms of log contention. If you have a hot row, everything queues behind trying to access that hot row, and the entire system slows down. At that point, just throwing resources at a problem is not going to solve your scalability issues. And how do you solve this? Like, how do you remain acid? And how do you continue to scale, to be available, and be consistent is the art of sharding, is how I would put it. And This is the place where we have spent most of our time debating, arguing, and what we have concluded. So there is a way to get the best of both worlds, to get both these things happening, and the way you do it is by understanding the relationships that exist in your database. And in other words, find out what relationships are strong in your database and keep them together. So when you shard, don't do it randomly. Don't just distribute everything and say, I'll build, a consistency model on top of it. Make your sharding smart. Make sure that, if there is a foreign key relationship between two tables, make sure you co-locate those rows in the same shard. So if you do that, then you get two things for free. You get single shard transactions, which means that the way they circumvent the cap theorem is by actually saying that data is not partitioned. They are together, which means that you get both consistency and availability for the data that you co-locate. So you get transactions for free, you get good indexing, and you get joins, all very cheap. And that is the way we recommend you do sharding. In places where it is not possible, there are workarounds. So, but then you still have to choose the happy parts very carefully. So far, so good. I'll briefly touch upon this. When you talk about isolation, there are many levels of isolation. On the extreme left, you have linearizable, which is the strictest and hardest isolation to achieve. On the extreme right, you have read committed, which is the easiest of them all. And these, by basically linearizable and serializable, so they are not exactly. I would say they are not like one is not an exact superset of the other, but in terms of difficulty of implementation, this is kind of how you see it. But typically, serializable applications don't scale just by the definition of what serializable is. Serializable essentially says it's as if everything happens one after the other in the strictest possible definition, and that by definition is not scalable. Linearizable has similar problems. And most of the time, when you talk about linearizable, serializable is implicit, but there are situations where it is not. Snapshot isolation is slightly less strict, but it has its own disadvantages. And read committed is the easiest to implement, but there are isolation issues related to that. I mean, if I drill down on this, the rest of the half an hour will not be enough to cover all these details. So I'm going to skip past this. But what I want to cover here is that this is isolation level is something that applications can be learned to tolerate easily. So if I say you only get read committed, you can still write very powerful applications using that. And the proof is that look at Postgres, right? Postgres default isolation level is read committed. Nobody has complained about that being a problem. That's because it is possible to write pretty complex applications with it. So the higher level isolation levels are not very useful. And in my opinion, they are not worth it in a distributed system unless you really, really have a strong use case for it. And if I say, oh, you will not have linearizable, you can find easy ways to work around it. So actually, as a matter of fact, I know very, very few use cases for where you say, oh, I cannot do this unless I have linearizable isolation level. So something to keep in mind. All right. So let us talk about Multigres. So a quick note about Multigres and Vitess. Although we are porting Vitess to Multigres, we are making a few changes. We are not just directly porting. There are things that we wished we had done in Vitess, those things we want to do for Multigres. So first one is we want full compatibility. If you use Multigres, it should feel exactly like Postgres right from the get-go. So from the beginning to the end, this is something that we want people to take for granted. Like If I move from Postgres to Multigres, I should not have to rewrite anything and everything should work as is. It's a very difficult goal to achieve, but we have set this high standard and we believe we can do it. The next one is approachability. Arka probably will know how approachable Vitess was, or Amit would know. Vitess was daunting to, if you go into Vitess, you have no idea where to begin. If something doesn't work, you have no idea where to start looking. You don't know what you've messed up in terms of configuration. We don't want any of that. We want Multigres to, you just install and it should just start running. And if there is a problem, it should be able to, tell you what the problem is and fix it easily. So that's another big goal that we have. And we are going to be a lot more opinionated about Multigres, which means that in Vitess, for example, there are 25 ways to do a backup. Vitess can accommodate any backup tool that you have, but in Multigres, we'll probably adopt one and we'll say, okay, just tell me you want to do a backup and we'll do it for you. Like 25 ways of providing to a backup, not many people need it. That's is something that we may change, but I don't think we'll need to change. I think people will love the fact that it just does it. It just works for me, so I don't have to worry about what tool it's using and how it's doing it and stuff. So that's kind of a different approach that we are using for Multigres compared to Vitess. But otherwise, we are copying a lot of code from Vitess directly into Multigres. I don't have too much time, so I'm going to quickly go over some of the highlights of what Multigres will do, and then I'll open it up for Q&A. I have lots of slides, so I'm going to do pretty quickly. So this is the basic Multigres architecture. Your application, if you had just installed Postgres, would have directly connected to the Postgres underneath. And then there would be a storage. Typically, if you are running a single Postgres instance and if it is in some respect some kind of production workload, your storage actually would not be a local NVMe, because if you lose that, then you lose all your data. You typically would use a DBS or some kind of replicated storage under the covers. What in this place, Multigres actually adds very little value for you, but it is just a starting point. What it will do is, at this point, will give you just connection pooling, right? So which anyway, all of us need. You cannot use Postgres seriously without any connection pool. So you get that. And more or less, the cost we think is going to be similar to what PG Bouncer is if you run it in this setup. The reason is because for a database, the highest cost is the number of network hops that it takes to get to a database. In this, there are actually two network hops. There are hidden network hops that you don't see. The first network hop is after you reach multi-gateway, you have one hop to the multi-pooler. The multi-pooler to Postgres is actually a local Unix domain socket, so that's not a hop. Then there is a hop to storage, and storage has its own additional hop because it's a distributed storage. So you're essentially looking at three hops here. And if you have a PG bouncer or something, you'll still have those three hops. You could do PG bouncer within the same instance, in which case you have two hops. And the reason why we have this is because this simple architecture, once you have this set up, once you've paid the price of this architecture, you can scale to hundreds of terabytes. The efficiency of the system remains the same, statically constant, and is not affected by how large you can scale. So that is the advantage of this architecture. And one simplification that we have done is in Vitess, if you wanted to spin up new databases, you had to provision those things by yourself and then tell Vitess, hey, by the way, I've provisioned these things. Start your VT tablets or VT gates. It was an extremely laborious and painful process. The way we are going to simplify it is basically bring up a component called the provisioner. In Kubernetes, it would be an operator. Once you have this, if you say create a database, it will do all the resource provisioning and make it extremely transparent for you. All right. The next one that Multigres problem that Multigres solves is high availability. So this is where the advantage of a multi-gateway, which is that second layer, comes into play, is that you don't have to change anything in your application when you say, I want high availability. So Multigres in that case spins up. So this DB Multigres is essentially this node, this entire node that you see here is what this DB represents. So it spins up these groups of nodes that are multi-pooler, uh, Postgres, and storage trios. And here is a primary, and then it has pooled, it has now spawned two replicas. And a multi-gateway can then route traffic to any of those depending on how you want to access it. You can say you still access multi-gateway as if it's a Postgres instance, but you can connect to DB1 at primary, which is a special name for your primary database. You can do DB1 at replica at your secondary database. And what you can do is uh, the the multi-arc is the new component that we have introduced, and what that does is do automatic failovers. And when those failovers happen, the multi-gateways handle the redirecting of that traffic to the correct primary, which means that your application has no knowledge of a failover. And usually, when the failovers are planned, then you will not even see an error being served. So that is the advantage of this proxy in the front, because it'll actually hold your transactions until the failover is done and then resume them on the new primary. Uh, and The one cool thing about this high availability, I don't know if you are aware of, I'm actually publishing a blog series about generalized consensus. What we are going to support is something called a durability policy, which means that you may say, this is my failure tolerance. Okay? I am allowed, I am okay with, like if I'm doing just a test instance, I don't care. I don't care about durability. There's no durability policy. Otherwise, you may say my data has to survive a zone failure, which means that I want if I do a commit and the commit is acknowledged, I want the data to be in a different zone at least, right? So you specify what you want in terms of your durability requirements. And what Multigres will do is actually make sure that that happens while at the same time respecting the laws of consensus. And that requires some rethinking of how consensus algorithms work. And that's why that big series is being published. And the other change we are making is I talk about true durability, which is in Postgres, it's not possible to implement a consensus protocol with the existing primitives that it has, which is the full sync wall replication. We are trying to see if we can make some modifications to that, which what I call as two-phase sync instead of a full sync, which will actually allow you to actually do durability the right way. It's a very deep subject. Unfortunately, I won't have time to cover this here, but feel free to ping me later or start a discussion on the Multigres project if you have questions about this. But the biggest advantage of this is once you have HA, once you have this durability, you don't need an EBS anymore. You don't need a mounted storage. You can just use local NVMe. And this will give you a huge boost in performance because then your IOPS become free. There's no network cost for basically accessing your storage. Your transactions will become super fast. Your joins will become super fast. And there is one more thing here. Because we have this proxy in the front, we can give you consistent replica reads, which means that you do a commit, the multi-gateway can keep track of that last LSN. And you say, I want to do a read, it can actually read from a replica, but wait for the replica to apply that LSN before reading your commit, which is kind of a cool way to distribute your reads and get consistent reads at the same time. I will be accelerating even further as we go. Uh, Multigres supports worldwide deployment. And the principle here that I want to highlight, I won't go into the details, is this complex looking design. Essentially, what it is trying to say is that if a cell gets isolated, it will continue to operate to serve traffic for as long as it can. As long as the data there does not gone stale, that cell will continue to do the best it can to serve your traffic. So that's the whole philosophy behind this design. Uh, and uh, and here you can implement your durability policies. You can say, if I have multi-cell deployment, I want cross-cell durability. You can specify these things pretty trivially, and Multigres will handle those for you. And if you have multiple cells and you have writes, you can also send your writes locally, and Multigres will know how to route those writes to the correct primary. It always knows where the primary is. And finally, in sharding, we are actually going to use a new philosophy, which is different from Vitess. We are going to introduce the concept of a table group. A table group is kind of similar to the Postgres table space. The Postgres table space is something that people don't use nowadays because it was relevant in the old days when you had fast disks and slow disks. Now all disks are the same speed. But you can think of a table group similar to a table space, which means that you can say this group of tables is in table group 1, this group of tables is in table group 2. But under the covers, what is a table group? Under the covers, a table group is either a single database, a single Postgres database, or a sharded Postgres, or a bunch of Postgres databases that are sharded. So this is how we do sharding. In other words, uh, a sharded Postgres is basically a group of table groups that are each sharded, but the logical view is that it is still a single database. So in this case, for example, there's always a default table group where all your tables begin. And as your tables grow, you create new table groups and you migrate existing tables to those. And those new table groups would be sharded, for example. If they are sharded, I say, oh, my shard is from 0 to 8 or 8 to infinity. This is like the hexadecimal based sharding scheme that Vitess has. And the advantage of this is you don't like if you want to change a sharding scheme, you just move your table to another a table group that has a different sharding scheme. So this makes it easy for you to move things around without without having to change the application. So the way this allows you to make sure that tables that are related stay together, which means that your transactions and your joins remain efficient, like I covered in the beginning. We have a few features that allow you to. There are things called reference tables. Like, for example, there are tables that are small that if you are in a sharded system, you want to make joins with. So those tables are called reference tables. And what Multigres will do is they will actually replicate those tables into each shard so that each join is local, for example. And there are also tables, there are situations where relational databases are complex by nature. Sometimes a table may have two foreign keys. There's a foreign key to table 1 and foreign key to table 2. And you want joins to for both against both to be efficient. That is physically impossible. But what Multigres can do is actually materialize this sharded table both ways and make both joins efficient. There is a price to pay, which is the second table will be eventually consistent. So that is something that you have to keep in mind. Unfortunately, in a distributed system, you cannot have everything. You have to choose your poison. And Multigres is going to be providing all kinds of migrations. This is going to be a superpower for Multigres. You can migrate into Multigres, out of Multigres. You can easily upgrade Postgres versions. We'll allow you to deploy safe schema changes, and we'll also allow you to do resharding. And there's something called the regret feature, which is a tribute to Slack, which where they say, oh, if I chose the wrong sharding key, what do I do? Well, uh, in Multigres, it will be as simple as, change the index on this table. So that's what we hope to achieve. And eventually, if you multiply shards by cells, this is kind of what your cluster will look like. But to the application, it should still look like a single Postgres. Where are we on the project? We are going to be doing connection pooling first, and next we are going to do HA. And Rafa promised me that it will be ready next week. I'm kidding. Yes, but it'll be ready very soon. Rafa is working on it. Once that is done, we will do NVMe support, which means that you'll get really, really awesome performance. Next, we'll work on migrations and finally sharding. I apologize for rushing through all this. There's a lot of cool things I could have talked about, but I want to give time for Q&A. So at this point, we are open.